So the problem we chose was 13.96. The tension in the spring is 0 when the arm APC is horizontal at 0. If the 100-pound block is released when at 0, determine the speed of the block when it hits 90 degrees and when it's at 180 degrees.
What I was expecting to happen is if our spring had a high enough K factor, I never thought that it would make it to 90 degrees or 180, and that it would just always bounce back up to this position right here.
Mm-hmm. I figured if the spring was strong enough, what would happen is as the weight moves down, the stored energy in the spring would bring it back up, surpassing 180 degrees. But whenever we test the system, we see that it really gets close to 180 degrees, but it does not surpass it due to friction in the system and gravity pulling it down. So the way that we found our K factor is by taking a 5-pound weight and hanging it on our spring. And what we did is we took the length of the spring after the weight was applied to it, and then we subtracted the initial length of the spring whenever it was not under a load. And whenever you take the force and then divide it by the change in the distance of the spring, then you get 0.95. Go. This is the online computer program Fiji, which is what we used to help us find the velocity of our weight as it reaches 90 degrees. So I'm going to give a brief demo on what we did to find that. So if we put our cursor here over our pinned connection, and then we create a line extending to the center of this weight, like so. What we're going to do is we're going to hit Analyze and then Set Scale. So it's saying that this distance is 306.0588 pixels. And measuring in real life, we know that arm is 12.875 inches. And what that does is it lets the computer know our scale. So now that we have established the pixel to inch ratio, we're able to properly analyze this video. So we took a slow motion video. We've got a stop clock here so that we know our time relative to how this weight is swinging. And we took that slow motion video and we imported it into a website that created photos for us out of the slow motion video, because that's what Fiji accepts as images to go through. So starting at frame 255, this is the first frame where our weight starts to drop at 0 degrees relative to the horizontal here. So 255 all the way down to frame 335. So the program allows us to find the difference in frames, which is 80. So what we said is we've got 80 frames between 0 degrees and 90 degrees. So in order to find our velocity, because it's not a constant velocity, what we're going to do is we're going to find 10 data points along this path, starting at 255, where we're going to say, all right, we're going to put our cursor here in the middle of this weight, And then we're going to cycle 8 frames and then draw a line between them to find the distance that it traveled. 1, 2, 3, 4, 5, 6, 7, 8. So move it along. There, that's in the middle of the weight. Then we record that value. Now we put our cursor back in the middle, like so, and then we cycle another 8 frames. 1, 2, 3, 4, 5, 6, 7, 8. And as you can see, the line is gradually getting just a little bit longer because the velocity is going to peak down at the bottom, or what would be the resting position of the pendulum. So you can see gradually getting larger. So we know that up here at 255, we have a time of 0.11 seconds, and at the very bottom at 90 degrees 335 we have 0.5 seconds. So the weight is moving for a total of 0.34 seconds. And what we're going to do is we're going to take an average time. So we're going to say, okay, we got 0.34 seconds, and we're going to divide that by our 10 data points. So the weight every 8 frames is equal to 0.034 seconds. So we've established our time, and the way that we find our velocity with the things that I've just presented is we're going to say, okay, between every 8 frames, we're going to take the change in distance over the change in time. And those values can be found in the spreadsheet. Another important thing to remember is that, as you can see, the cursor, I'll bring it back up to 255 here at our starting position. There's a little bit of subjectivity to where the center could be, and that slight amount in variance could total up over the trajectory of this pendulum. So what we did is we went through this process 4 different times and took an average to try and be as accurate as possible. So after using Fiji 4 different times to find our real world velocity, we get an average of 7.131, and that's pretty close to what we calculated. We were predicting it to be about 8.12 feet per second. So we get a difference of about 1.02 feet per second, and it's a little bit difficult to imagine things in feet per second because it's not a unit that we're used to. So looking at it in miles per hour, we're getting a tolerance within about 1 mile per hour, which is relatively accurate. Another thing we'd like to address in this section is that our total length average for all of our tests comes out to be 19.34 inches, which is a little bit short of what it should be. It should be closer to about 20.22 inches. And the reason for that is because we're using straight lines along a relatively curved path to try and calculate our velocity. And of course, it would be better if Fiji software allowed you to make curved lines instead of just straight lines. But nonetheless, this is the most accurate way that we are able to find the velocity of the arms it's swinging at the 90-degree position, because we attempted to use a velocity gun, but the velocity gun did not register at the speeds that we were trying to find. And another thing is that we know that the velocity is relatively accurate, and we know that because we would expect our real world velocity to be just a little bit slower than the calculated one due to friction. So our mathematical prediction was that the arm, as it swings through back up to the 180-degree position, that its velocity would be 0. And looking at the slow motion clip, that is what we find, is that the velocity is 0 at its highest position, even though it doesn't quite reach 180 degrees.